Okay, so yesterday's assignment hopefully was relatively simple, but there's some typical ones that you might run into trouble with. So when you get to question 6, so if you've ever had like a sonogram, so on that one, so like here's your leg, and they're gonna have the device that's gonna send out these waves. So basically the
You can't see your masterpiece,
Don't.
your neo-expressionism art on
that's not bad, okay. Anyway, so and it's pretty cool, basically, if you look at how sonograms work, or sonograms, or anything like that, because basically you're taking a sound wave and turning it into a picture, okay? And that's basically how it works. So you're gonna take one type of medium and run it through an algorithm and go, oh, this is what this looks like. And we do the same thing in space, like X-rays, radio waves, and when we study outer space. What we get in terms of like a radio wave or an X-ray or something like that, we can't see because of the fact that we can't see in that spectrum. But you run it through an algorithm and you say, oh, this is an X-ray, but this is how we can visualize it. So the whole key on this one pretty much is nothing more than, hey, can you understand what's going to happen? So you're 12 centimeters below the skin, right? So how far does the signal actually have to travel before it gets back to the machine?
Double the distance.
Yeah, so it's got to go down, hit the object, and then bounce back. So your total distance traveled is actually going to be 0.24. Now, the question being is that what's the minimum time between impulses? How many pulses per second? So on this one, there's more and more you're going to have to use your book to look up data. So if you look in your book on page 474, there's a chart that says, oh, this is how fast things travel. So you notice on ultrasound, that's at 1,540 meters per second. Well, if you consider the speed of sound is 350, roughly, so in ultrasound, that's like 1,500. So sound traveling through your skin and that or tissue is roughly about 5 times faster than it is now, okay? So, and again, if you look at the mechanism on how sound travels, because it's a series of compression waves, so your skin and your flesh is able to transmit those waves easier than air does, and that's why it's so much faster. And anyway, so in terms of pulses per second, you should be in the 6,000 range of pulses per second, okay? Which is quite a few if you think about it. Well, that's a lot. Speaking of 6,000, your answer to number 4 should be around 6,000. That's an ish. Yeah. Your answer to number 2 should be around 100. Okay. When you get to question number 4, no, question number 5. Wave pulse travels on the screen. So there's 2 kind of things that you need to get out of question number 5. So when you're looking at that equation, that velocity equals the square root of tension divided by that mass per unit of length, that is not the speed of sound, okay? that is how fast something is traveling like along a string, okay? So if I take that banjo and I hit different chords, that speed is gonna travel different values on the string itself. But once it turns into sound, it's all gonna travel at 343 meters per second. So when you look at that equation, that is not the speed of sound. That is the speed of an impulse along a string medium, okay? Not the same thing. All right, anything else? All good? Once, twice, so, Danny.
Number 5, does it, or what's like the speed of sound in water?
Oddly enough, Danny, if you
It's in the
look over
book.
here on page,
It's also in the back.
wherever that is, 474,
Yeah, no,
there's
that's
the
what I
speed
use.
of water. 1,480 meters per second.
Okay, we use that one instead. Because I use 1500 by like doing a quick web search.
No, you've got to
Okay,
use the
got it.
numbers, because that's what I'm gonna base
And I would
the
agree.
calculations off of.
Okay.
Pop that out.
It's 14 or
Yeah,
1480.
it's faster, so
Thank you.
11 milliseconds is.
All right, Andrew, stop.